This is lesson 3.5 on multiplicities of zeros. So we've been discussing real polynomials. A real polynomial, that's a polynomial where our constant and coefficient terms are all real numbers. So they are not complex numbers. So there are no i's involved with the coefficients. Now we can talk about complex polynomials, where that's going to be polynomials where the coefficients and constant terms are allowed to be complex numbers. That's beyond the scope of our class, so we're not going to worry about those, but such things do exist. Whenever we are working with real polynomials, a nice fact about the real polynomials is that we can always factor them into linear and irreducible quadratic real terms. So the linear terms and quadratic terms are again real in the sense that all of the coefficients and constants that we see are real numbers. However, those irreducible quadratic terms, those are going to correspond to complex zeros. Remember last time we saw that there's this relationship between zeros and factors. For every linear factor, there's a corresponding zero. For every quadratic factor, there's going to be two corresponding complex terms. And we'll see those in a moment. Now when we fully factorize a polynomial, and that's not an easy task, fully factorizing a given polynomial actually takes a fair amount of work. We will need to be able to do that for fairly low powers, maybe fourth power polynomials, fifth at the very most, but most likely the fourth is the highest that we're going to be working with. However, once we are able to fully factorize the polynomial into linear and irreducible quadratic terms, it is very easy for us to identify the zeros of the polynomial as well as what we call the multiplicity of the zeros. So what we mean by the multiplicity is that if we look at the fully factored polynomial, the zero, if we look at its corresponding term in that factorization, the exponent of that term is going to be the multiplicity of the zero. So for example, if in our factorization we have an x minus 1 cubed term, that means that the zero x equals 1 has a multiplicity of 3. Now one of the nice things about multiplicity of zeros is that if we look at the multiplicity of each zero and add up those multiplicities, it will always equal the power of the polynomial. If we multiplied out the polynomial completely, the highest power of x, that would equal the sum of the multiplicities of each zero of that polynomial. And we're going to use that to our advantage sometimes. If we're ever unsure if we have fully factored a polynomial, we can just look at the multiplicity of the zeros and recognize that yes, we have them all, or no, we need to keep going. Now we are going to work with easy problems for the drill. For the drill, we're already going to have the polynomial factored into linear and irreducible quadratics. In our application problem, we're going to handle a polynomial where that's really the grunt of the work, the most of our work there. Here's a whole polynomial that's multiplied out. We need to factor it. We'll look at an interesting technique that we can use to narrow down our search. But it will take a little bit of time. So we'll start with the easy, quick drill problems and spend a little bit more time looking at how to fully factor a polynomial. Okay, so let's consider this drill example. Now before we get going, let me just go ahead and warn you that these are absurdly easy. I almost feel ridiculous giving these to you. However, I want you to keep in mind that what I'm wanting to reinforce with these problems isn't the difficulty of these problems themselves, because again, these are very, 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 very simple. What I'm wanting to reinforce is this connection between the zeros of a polynomial and factors. For every zero, there's going to be a corresponding factor of that polynomial. So the way we are going to do this is we look at the polynomial that has already been factored for us. For the drill problems, they will already be factored. For the application problems, we're going to have to spend more time to actually factor these. But for the drill ones, they will be pre-factored. So here's what we do. Look at each of these guys. So x minus 1, x plus 2, and x minus 5. We're basically wanting to find where do each of these equal 0. You do not need to write this out, just to be crystal clear as to where we're getting these things. So x minus 1 is 0 when x equals 1. X plus 2 is 0 when x equals negative 2. X minus 5 is 0 when x equals 5. So these are the three zeros that we're finding, 1, negative 2, and 5. The multiplicities are going to be the exponents of the corresponding factors. So the multiplicity of 1 is going to be 3. So x equals 1 is a 0. And for the multiplicity, you can just put m3 in this case. So the multiplicity here is 3. X equals negative 2 is our next 0. The exponent of x plus 2 is to the 5th. So the multiplicity of this 0 is just going to be 5. So multiplicity equals 5. And last but not least, x equals 5 is a 0. There's no number here, so it's an implied 1. So the multiplicity here is 1. So that's it. That's all there is to these problems. When all we have are these linear terms, they are absurdly easy. But I want to focus on this relationship between zeros and factors. That's a very important concept. Another nice thing that we know about this polynomial, we said before that the number of zeros, when we take into consideration the multiplicity of the zeros, that's going to equal the power of the polynomial. So notice here, 3 plus 5 plus 1, that's 9. So if we were to multiply all this out, it would be a degree 9 polynomial. Our first term would be something times x to the 9th. So two things that are important here, the relationship between factors and zeros, and this idea that the multiplicity, the sum of the multiplicities, is going to be the sum, the sum of the multiplicities is going to be the degree of the polynomial, the highest degree of x when we multiply everything out. So here's another one. Notice that this one is a little bit different than the previous one. Here we now have an irreducible quadratic. What we mean by irreducible is that x squared plus x plus 1, there is no way that we can write that as the product of two linear terms using real numbers. So in other words, what that means is that this quadratic has no real roots. The only time that this is going to equal 0 is if it equals a complex number. So this is significantly different from when we're dealing with our linear terms. So we do need to approach this in a different manner. We get an easy answer here for the linear term. We get x minus 3. That's going to give us a 0 of x equals 3 with multiplicity 2 in this case. So we get a quick and easy answer there, but that's not the full answer. We need to worry about the quadratic portion. So how do we solve where a quadratic equals 0? Well, if we can't factor it, which is the case here, remember our fallback method is going to be to use the quadratic formula. So here, everything is 1. A is 1, B is 1, C is 1. So using the quadratic formula, our x is going to equal negative b, so negative 1, plus or minus the square root of b squared, so 1, minus 4 times a times c. So 4 times 1 times 1, so 1 minus 4, all over 2a, and again that's just 2 times 1, so 2. So this gives us negative 1 plus or minus the square root of negative 3 over 2. This tells us, aha, we have a complex solution. So our two solutions are going to be negative 1 plus or minus I square roots of 3, all over 2. Now I would expect you to do something like this quickly, and I would like for you to recognize that this negative comes out as an I. Remember, I'm a little bit more lenient about factoring out correctly the square root numbers. I still would like for you to be able to do that when necessary. But here, the only thing that I'm really going to be very strict about is that that negative needs to come out as an I. So what we have here is, notice we have two zeros, negative 1 plus I square roots of 3 over 2, and negative 1 minus I square roots of 3 over 2. We will always have complex solutions coming in pairs. We will never get one of these on its own. So you're welcome to keep these grouped together as a pair. That's perfectly fine. So our answers here then, we have x equals 3, which has a multiplicity of 2. We recognized that earlier. Here's the corresponding factor. Here's the power. So that's where the multiplicity comes from. And then we have 2 different zeros here. You can write them together, but I want you to be aware that these are 2 different zeros. So x plus I squared roots of 3 over 2, and negative 1 plus I squared roots of 3 over 2, and negative 1 minus I squared roots of 3 over 2. Each of these have degree 3, or multiplicity 3. So notice that the overall degree of the polynomial then is going to be 2 plus 3 plus 3. So a total of 8. We add the 3 twice because this is the multiplicity for 2 zeros. We'll keep them together because we'll always have them coming in pairs, but when we consider the sum of the multiplicities, we treat them separately. So the total degree of this polynomial isn't 5, it's going to be 8. 2 plus 3 plus 3. But this is our final answer. Here are our zeros and their multiplicities. Alright, so here's a little bit more difficult one. So find the zeros and their multiplicities of x to the 5th minus x to the 4th minus 18x squared. So same instructions, but the obvious difference this time is that the polynomial is not factored for us. So here's how we can approach these types of problems. First things first, if you notice a common factor between every term here, go ahead and factor it out. Always be, I shouldn't say this, but always be lazy. Do the easiest thing first. So if there's something you can do to make life easier for you, do it. So in this case, notice that everything has an x squared term in common. So I'm going to rewrite this as what it looks like when I factor out that x squared. So x to the 5th, that becomes x cubed, minus x to the 4th, that becomes x squared, minus 18x squared becomes just minus 18. Okay, so x squared, that helps us out. This actually tells us one of our zeros already. One of our zeros is, well, 0. And furthermore, it's going to have multiplicity 2. So let's go ahead and make note of that. We know that x equals 0 is a 0, and it has multiplicity 2 because its corresponding factor, which is just x in this case, has power 2. Okay, to find our other zeros, we need to look at this right here. Now, since this is a cubic term, we know that it can be factored. We don't know how exactly, but anything that's cubic or higher, we can always split into linear and irreducible quadratic terms. So here's how we can narrow our search. Rather than just trying to think of every single number that might work, let's narrow down our search to things that can work. Here's what we have to do. This is what we call our rational root theorem. If we have any zero for this polynomial, it has to be of the form p over q, where this top number p has to divide this number right here, the constant term, and this number q has to divide whatever number is right here, what we call the leading coefficient. Now, just to help us out a little bit, I'm always going to give us problems where the leading coefficient is 1. So we actually don't need to worry about q in this case. We only need to worry about p. So in other words, we only need to worry about numbers that are factors, rather that divide, same thing, into 18. So we want to check, let's go down the line. 1 will go into it, well actually plus or minus 1, plus or minus 2, plus or minus 3 will go in, 4 is no good, 5 is no good, 6 will work, 9 is the next one, and 18 is the last one. So this isn't very good news. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different things that we can check. Well, at this point, unfortunately, we've just got to sit down and do it. Unless you have a graphing calculator. If you have a graphing calculator, you can kind of cheat. You can have your calculator graph this, and it will tell you, okay, here's where it equals 0, so you can narrow down your search. Let me just give you a few examples of things that don't work, then we'll cut to the chase. Let's try just take a look at what does x equals 1 and x equals negative 1 look like. Remember from what we talked about last time, If this is a 0, then x minus 1 is a factor of this, and vice versa. So let's just plug in x equals 1 to see if this equals 0. So 1 cubed minus 1 squared minus 18, so that's going to be 1 minus 1 minus 18. Yeah, that's not going to be 0. That's going to be negative 18. Negative 1, very similar story. If I plug in negative 1 for x, once again, I'm going to get, let's see here, negative 1 minus 18, so negative 20. Once again, it's not 0. You can do the same thing for 2, plus or minus 2, plus or minus 3, plus or minus 6. You can go through each of these. I believe what we're going to see from this, let's look at x equals 3. I'm cheating here. But in actuality, you'd probably just need to go down the line with these. Use your calculator. Again, for these application problems, you can use your calculator. I encourage you to make good use of them. So let's try x equals 3. So when I plug in x equals 3, I get 3 cubed minus 3 squared minus 18. So that's going to be 27 minus 9 minus 18. So 27 minus 9 is 18. 18 minus 18 is 0. So we found a 0. That means we found a factor. So if x equals 3 is a 0, that means that x minus 3 is a factor. What we're going to do now is we're going to divide this polynomial by x minus 3. Since this is a linear term, we can use synthetic division. So let's use that. So synthetic division, we're going to put 3 in the box, 1, negative 1, 0, negative 18. Remember, the 0 is from my x term. I don't skip any terms. So synthetic division, drop down the 1. 3 times 1 is 3. This gives me 2. 2 times 3 is 6. 6 plus 0 is 6. 6 times 3 is 18. All right, good. This is a good double check. Whatever I get here should be 0. So this means that my polynomial, x squared I already knew as a factor, but we now know that x cubed minus x squared minus 18 I can write as x minus 3 times the quotient that we found right here. My highest power before was x cubed, so this is x squared. So x squared minus plus 2x plus 6. Okay, so we've got a linear term here and a quadratic. I now need to see if this quadratic factors. If it doesn't, I still need to find where it equals 0 just so that I can say what the roots of this quadratic are. So I'm going to, let's see here, I'm going to erase this over here to make a little bit more space. So what's the easiest way to find where a quadratic equals 0 if I can't factor it? Just go ahead and use the quadratic formula. If you look at it and you're not sure if you can factor it or not, just go ahead and use the quadratic formula. So this is going to be 0 when x equals, so a is 1, b is 2, c is 6. So x equals negative b plus or minus the square root of b squared, so that will be 4, minus 4ac, so 4 times 1 times 6, so minus 24 all over 2a, so that will be 2. So this is negative 2 plus or minus, this will be square root of negative 20 all over 2. So this negative 20, square root of negative 20, when I take the negative 1 out, that becomes an I. 20 I know is 4 times 5, so when I take the 4 out, it becomes 2. So the square root of negative 20 is the same as 2i square roots of 5. So now when I divide everything by 2, I'm left with negative 1 plus or minus I square roots of 5. And at last, I'm done. I know my final answers now. So we recognized early on that x equals 0 is a 0 with multiplicity 2. X equals 3 is a 0 with multiplicity 1. Notice there's no exponent here, so it's an implied 1. And then my two complex zeros, I can keep them together. X equals -1 plus or minus I square roots of 5. And each of those have multiplicity. Again, there's an implied 1 here. So the multiplicity is 1. So a good quick check. Add up the multiplicities. Make sure it equals the power of the polynomial. So 2 plus 1 plus 1 plus 1. Again, I add this twice because these are two zeros here. So 2 plus 1 plus 1 plus 1 is in fact 5. This is a long problem. However, there's a very good chance that we are going to see it on the application portion. This is an important concept, so I would make sure that you understand how to approach these. It is complicated. There are several different parts to this problem. That's really what makes it so difficult. But if you keep in mind, our end goal here to get the zeros is to actually find the factors. If we can find the factors, then the zeros are no problem whatsoever. But getting it fully factored is easier said than done. Keep this in mind. Take out the easy things. When you're not sure how to proceed, remember that the corresponding zeros are going to have to be a factor of this last number. So in this case, it wound up being a factor of 18. For the test, I'll most likely make life a little easier for us, maybe narrow it down so that there are only maybe 6 or 8 factors instead of, what do we have here, 18 different factors, or rather 12 different factors. There will still be more than just 1 or 2, so it will take a little bit of work still. But you should be able to do it without too much difficulty, particularly if you have a calculator to help you through it.